In machine learning, evaluation metrics are essential for understanding how well a model performs. One of the most fundamental tools for this is the confusion matrix. In this video, we'll break it down in depth, from basic definitions to real-world applications. A confusion matrix is a table used to evaluate the performance of a classification model. It compares the actual values with the model's predicted values, helping us understand where the model is getting things right or wrong. In binary classification, the confusion matrix has four key values: true positives, false negatives, and true negatives. True positives, or TPs, are cases where the model correctly predicted the positive class. For example, predicting a patient has a disease, and they actually do. False positives occur when the model predicts something as positive, but it's actually negative. This is also called a type 1 error. A false negative happens when the model predicts negative, but the actual value is positive. This is known as a type 2 error. True negatives are the easiest to understand. The model correctly predicts the negative class, and it truly is negative. Imagine you're building a spam filter. Emails labeled spam or not spam create a binary classification problem. Let's map these labels to the confusion matrix. If 5 spam emails were correctly caught, those are true positives. If 3 important emails got marked as spam, that's a false positive. The term confusion comes from how the matrix reveals what the model is confusing, like mistaking real emails for spam. From the confusion matrix, we can calculate key metrics like precision and recall, two essential tools for assessing your model. Precision tells us how many of the predicted positives were actually correct. High precision means few false positives. Recall shows how many actual positives were correctly predicted. High recall means you're catching most of the real positives. Precision and recall often trade off. Improving one may reduce the other. It depends on what matters more in your use case. To balance precision and recall, we use the F1 score, the harmonic mean of both. It's a single metric for model quality. Confusion matrices aren't just for binary tasks. For multi-class classification, it becomes a larger square matrix, comparing every class. A confusion matrix can be visualized as a heat map. Darker colors indicate higher values. This quickly shows patterns and errors. One pitfall is misinterpreting accuracy. A model with 90% accuracy could still be failing if the data is imbalanced. Imagine a data set with 95% non-spam and 5% spam. A model predicting non-spam always would be 95% accurate, but useless. To address imbalance, use methods like oversampling, undersampling, or weighted classes. Evaluation metrics like F1 and ROC-AUC help too. In Python, you can generate a confusion matrix using scikit-learn. Metrics, confusion tolerance matrix. Let's see a quick example. You can also use confusion matrix display to plot it neatly. In cancer detection, false negatives are very dangerous. We'd rather have more false alarms than miss real cases, so high recall matters more. Let's review. TP, correct positive. FP, wrong positive. FN, missed positive. TAS, correct negative. Use the confusion matrix to gain granular insight into your model's strengths and blind spots. It's more than just an accuracy score. The confusion matrix is one of the most powerful tools in your ML toolbox. Mastering it means mastering your model's behavior. Thanks for watching.